Hello everyone, this is Dr. Mo Shiva, Professor of Electrical Engineering at California State University, Fullerton. Purpose of this video is reviewing nodal analysis. This is the third of the three videos related to nodal analysis. If you have not seen the first two videos, please go and start with those. Review video 1 and watch video 2 and then come back here. For this example, we have a circuit which has different types of sources. To do just a quick review, we choose a reference node which can be assumed to be ground. It doesn't have to be, but we treat it as if it has 0 volts. Assign voltages to non-reference nodes. These are already done on the figure. If there are any voltage sources, we use supernodes. Then we apply Kirchhoff's current law to non-reference nodes and supernodes. Preferred version, summation of currents leaving the node equal to 0. And we never apply Kirchhoff's current law to reference node. Circuit here has independent and dependent sources. We want to find nodal voltages and the power supplied by 5 volts and 5 amps source. So first thing to do, we look for voltage sources and we form supernodes. We see one between nodes 3 and 4, so we have one supernode there. And there is another one between node 1 and reference. However, we never apply Kirchhoff's current law to the reference node. And in fact, a voltage source being connected to reference node is very useful. Looking at the 5 volt source, it is telling us its positive side is 5 volts above the negative side. So basically, V1 is 5. For supernodes, we look at Kirchhoff's current law applied to the supernode, and then we look at inside supernode. See what is going on inside the supernode as described in second video. So here we just look basically inside the supernode. Supernode is V1 and reference. Since reference is there, so we simply use the information provided by the source, and that is telling us V1 is equal to 5. Let's go to node 2. Current leaving from node 2 to the left is just 1 amp. So we have 1. Add to it the current going straight down. We're using passive conventions. So that is V2 over 2. And current going down on the right-hand side branch, we need positive on the top and negative at the bottom of the 1 ohm resistor. In other words, V2 minus V3. So we have V2 minus V3 divided by 1 equal to 0. Let us call this equation 1, and we will come back to it. And then we look at supernode. Supernode has nodes 3 and 4 in it. I'll start with one of the branches. Let's start with the branch, the 5 ohm branch. Write currents leaving the node equal to 0, and just move along the red line encircling the nodes and write the currents leaving that supernode equal to 0. So first term is V4 minus V1 over 5. To find that current, we need the positive at the bottom, negative on the top of the 5 ohm. So that's V4 on the positive side, subtract from it V1 on the negative side. Going straight up, we're looking at negative 5 amps leaving the node. Next term we have V3 divided by 2. And between node 3 and node 2, we're looking at V3 minus V2 over 1. And the whole thing is equal to 0. Let us call that, let me squeeze it in here, let's call this equation 2. Immediately after applying Kirchhoff's current law to the supernode, we look inside the supernode. Inside the supernode, we have a voltage source, positive on V4. So V4 negative connected to V3, so V4 minus V3, and it's given to be 2 Vx volts. At this point, we look at Vx, see where it is defined. It is across the 1 amp source on the top, positive is on V1, negative on V2, so V1 minus V2. The only place that Vx shows up is here. So let us substitute Vx in that equation and simplify a little bit. One thing that I have mentioned in previous videos is we can always check for a sign mistake quickly if we use currents leaving a node equal to 0. So if you're looking at node 2, the term should involve positive V2. So positive V2 or positive V2 minus another nodal voltage. For supernode, that involves nodes 3 and 4. So the terms should start with either positive V4 or positive V3. So if in the last term, instead of V3 minus V2, we had V2 minus V3, we know we need positive V3, and we would quickly pick up that sign mistake. All right, let's substitute Vx in that equation. Left-hand side can be written as negative V3 plus V4 equal to 2Vx, or minus 2 Vx being V1 minus V2 equal to 0. Simplify that. We get 2V1, 2V2 minus V3 plus V4. Since V1 is known, take it to the right hand side, is equal to 2V1, which is 5. So 2 times 5 is equal to 10. Let's call this equation 3. We have equations 1, 2, and 3. Let's simplify those and write them next to each other. First equation gives us 1.5 V2 minus V3 equal to -1. So that's our equation 1. Second equation, simplifying that, we have negative V2 plus 1.5 V3 plus 0.2 V4 equal to 5 plus V1 over 5. V1 again is known, so 5 over 5 is 1. That gives us 6. That's our equation 2. Third equation, 2V1, 2V2 minus V3 plus V4 equal to 10. So 3 equations in 3 unknowns. Equation 3 can be used to find V4 in terms of V2 and V3. So equation 3 gives us V4 equal to negative 2V2 plus V3 plus 10. V4 does not show up in equation 1, so let's substitute that in equation 2. Equation 2 becomes negative V2 plus 1.5 V3 plus 0.2 V4 and we are substituting for V4, so 0.2 times negative 2V2 plus V3 plus 10 equal to 6. Simplify that and we have negative 1.4 V2 plus 1.7 V3 equal to 4. So we have 2 equations, this last equation and also equation 1 in terms of V2 and V3. 2 equations, 2 unknowns. So let's solve that system. Equation 1 is (1.5) V2 minus V3 equal to -1. And the last equation is negative 1.4 V2 plus 1.7 V3 equal to 4. Let us eliminate V3. Multiply the first equation by 1.7. We get 2.55 V2 minus 1.7 V3 equal to negative 1.7. Second equation doesn't change. And let us add these equations together. V3 will cancel out. It will end up with 1.15 V2 equal to 2.3. So we can find V2. So V2 is 2 volts. From equation 1, V3 is 1.5 V2 plus 1, and that gives us 4 volts. And using equation 2, V4 is 10 minus 2 V2 plus 3. Substitute for V2 and we have 10 volts. So we have the nodal voltages. At this point, everything else is straightforward and easy to find. The problem is asking for power. Again, we use passive sign convention, and power usually refers to power absorbed by the element. So if we have an element with voltage V across it and current I entering positive of V, absorbed power is V times current entering positive reference of V. So let's look at the figure. We want to find the power supplied by 5 volt and 5 amp sources. So for 5 volt source, let us find this current. Current entering is positive, and that would be 1 amp coming from the top plus the current going straight up. So we want to find I1. That would be 1 plus, let's call this I2. Kirchhoff's current law at node 1. We want to find I1, it's 1 plus I2. So power absorb, we don't have to write it. If we say power, we're referring usually to absorbed power, is 5I1. That is 5 times 1 plus I2. That is 5 times 1 plus, let's look at I2. I2 is going up in the 5 ohm resistor, so we need voltage divided by 5. Voltage positive on V4, negative on V1. So V4 minus V1. V4 minus V1 over 5. That is 5 times 1 plus 10 minus 5 over 5. 10 watts, that is the absorbed power. Since we have used passive sign conventions, supplied power is negative of that. So P 5 volts is negative 10 watts supplied. So as you see, that source is not really supplying power, it's in fact absorbing power. So the source is being charged. For 5 amp source, if we use that polarity For the voltage, we are talking about V4, and the current is going out of the positive. So that voltage gives us the supplied power directly. So power supplied by 5 amps. Remember, whenever we calculate the supplied power, we have to make sure we write it down. Otherwise, P equal to VI is usually referring to absorbed power. So that's 50 watts supplied. Now that is the end of the example. Review examples 1 and 2, videos 1 and 2 for nodal analysis. We will have further videos for other methods of circuit analysis, mesh analysis, superposition, Thevenin-Norton's theorems, and whatnot. So this covers basically nodal analysis, and you can look at the videos for future topics later.